So I will talk a little bit about the noise protocol. That's a standardized protocol, a security protocol, and we use that heavily in our aeternity blockchain, you could say. So you can imagine that security is a kind of an issue in blockchains, right? You want it to be reasonably secure, at least. So I got interested in that kind of security last summer. So okay, how do we do this? How do we actually make sure that we have top of the notch security in the things we are building? And I was learning a bit more about that security. And I want to tell you a little bit, take you on that travel. What are you able to do nowadays in the security area? What did we do for this particular noise protocol, and a little bit of what could be done in the future. So we send transactions and blocks, and in state channels we talk, Alice talks to Bob, and all that kind of communication in aeternity is done over the noise protocol. Okay, so that's something slightly easier than TLS. And why would you do that kind of sending blocks not over HTTP or just sending it by email or whatever? I mean, you can do all kinds of stupid things. But why would you want to have a secure protocol? Well, because in principle, you could then say, I don't want to talk to you anymore if you start spamming me. If you first have to make a connection to someone and you have to secure that connection, you say, if someone is sending me rubbish, I can stop talking, and therefore I save bandwidth. That's the main idea there. And in all situations, you really want to have security. So, not saying too much about that. Noise is something which came after TLS. TLS is when you have HTTPS in your browser. That's when you talk TLS. It is the same kind of principle, Duffy, Hellman, crypto, key exchange, etc. But it's much more simplistic, you could say. It's easier to use, it's less configurable, so it's lightweight and therefore faster. And it also has a few kind of security bugs that they have in TLS you don't have here anymore because it's new. But we use only the Checkin 20 Poly 1305 cipher suite, right? That's what we use, and never mind what that is. But that's part of this enormous protocol, and that's what we use in aeternity. So this is how the stack looks like. So in the bottom, you can run it on an operating system. We normally use either the Mac OS or Linux. There's also a Windows version. Is it already out, Tino, or is it soon available? Or no? It's out. See? But you can even run this on Windows. I don't know. I guess Libsodium is the crypto library. That's a C library, also called as NaCl or whatever. So it's used by Firefox, for example. It's a crypto library used for all those crypto curves. That's the heart of the thing. That's where the crypto happens, and that is done in C code because the crypto stuff has to be very fast, and C is a very good language for doing that kind of bit operations very fast. So that's where you have the C stuff, and then if you want our stuff, the top one, aeternity, is programmed in Erlang, as you probably know. So you want to talk to that, and you do that in two steps. First step is you have a binding of the C code to Erlang, and that's called the eNuckle library by Jesper Louis Anderson, that you probably have heard about, well known in the Erlang world. So he made a binding between Erlang via NIFs, native function interface, to the C code. So that's that part. And then on top of that is the actual eNoise implementation in Erlang. And that's by Hans, who's sitting in the corner and carefully listens whether I don't say any super stupid things. So he implemented the noise protocol in Erlang on top of that, and on top of that is our peer-to-peer sync protocol, is our state channel protocol, whatsoever. Now, question, where in the stack do we expect most security errors? Obvious?
Linux.
Sorry? In Linux. Well, if there had been Windows, I would say yes, of course. Now, if you wanted to, say you have only a week, and you want to focus on something to find security breaches, and you want to find something, I would say, look in the newest thing, right? This was the newest thing, and that's very new. So here you would expect most things to happen. On the other hand, all the cryptography is done here. So you also want to look at that. You can spend ages analyzing Linux and try to find security breaches there, you will, but it's kind of not what I had time for. So we started bottom up. First looked at libsodium. Is there anything we can do there to find security vulnerabilities? Then we looked at eNACL. Is that something we can find some security breaches? We looked at eNoise and we looked at aetenity PTP. Now I'm probably most going to talk about this part because I think that's really cool. But we did look at the different levels. So this was joint work with Martin Mori and Santiago Zanella Beguiling from Microsoft Research and the University of Paderborn. I was together with them for a week and did this. So libsodium, what can we say about that? It's C code. I had those researchers with me, and they knew all kind of static analysis tools to find security breaches. So I said, oh, let's run the latest and greatest and nicest static analysis tool for C code, just out of the box. See what we find. So they have a tool called Scan Build. That's part of the LLVM, whatever suite, and they switch on all the possible options they had, and all the default options and whatever, and they will check the code and run that over the C code, and you get all this static analysis. And since libsodium is very well known and used by lots of people, we did not expect to find a lot of things because it's so well used. And indeed, we did not find a lot of things. We only find 17 possible security breaches. Now, 17 may not sound like a lot of things, but you have to look at them, each and every of those security breaches separately. Right? You have to look into them. Is this really something, or is it just the tool that says, oh, this might not be secure, but actually those guys know what they're doing. So I'll give you a number of examples of what C programmers do. Anyone here C programmer? Okay, so I should be very careful what I say.
Don't worry, I'm not happy.
Okay, good. So, this was one of the things that you get out of the tool, and then you can analyze it. And what you do, you have lots of arguments here for a C function. And one of the things you send here is the CTX. It's a pointer to some kind of crypto, AU, blah, 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 GM state. Yeah? That's super nice, that's a pointer. And then you cast that pointer to something of the type context. And then you put that in. And then you take the field in that apparently struct. But what was this? So if you look at this type, it's actually just a byte array. So you send the byte array, and then you cast it to a struct, and then you read the pointer. Now I always get a bit nervous about these kind of things if I see them. The tool as well. But people that program C for a living, they say, ah, that's fine. Writing a that's fine. Of course you do it like that. Much more efficient. So, okay, so this is how you write C code, and then C programmers are tough guys, so this is how you should do that. But here they're using RKey, and who guarantees us that that is not kind of overrunning the memory, reading the wrong part of the memory, whatsoever, right? Giving it a null pointer exception, all that stuff. So you have to know what the struct is like, and this is 16 something, and then there's another 16 bytes here, and you have to take the right ones from that big array. How do you know that you do that? Well, you have to analyze that. So you have to, by hand, start looking at it and thinking about it and say, yeah, indeed, this is big enough, and you don't do that, and you do that, and therefore this is okay. And each of those 17 issues takes some time, right? So that's what you have to keep in mind. So it's cool, but it takes some time. We have another one where these tools are actually quite smart. So they have a finding here that they say, well, down here, you have an I2A64, and you take the nlog2 index of that array. Now that is only good if that nlog2 is actually in a certain bound, right? Because this array is a constant with 64 characters in it, and you take one of those characters. Super smart C code, people do that kind of things. But if you have n log 2 65, then you have a problem. Minus 1 is also a problem. Well, there are more problem numbers than actual good numbers. But of course, then you have to find out that this is actually not the wrong number. So you reason backward. How can I get here? Well, I can only get here if I do not take this branch, right? Because if this branch is true, then I return null. So that I will not do this. And then I can only do this. But I see it's already not greater than 63, because if it would have been greater than 63, I would take this branch and I would return null and I would never get there. So this is the kind of reasoning you have to do when you see these kind of things. And you do that, and you hope you make no mistakes in your reasoning, or actually, you can let the computer do this, right? There are nowadays model checkers that actually can explore the complete state of a C program and just symbolically compute whether or not a certain point is reachable and with which values it is reachable. So what you do then is you instrument the code, you look at the code a little bit and you instrument it and you say, well, look, I added assertion here, so can I get here, and then you from here to there, can I get actually into that position and with which values. You run your model checker for a while and it says, you implement your assertion here, and your assertion says, if I ever get here, then I'm in trouble. And says, no, it's unsatisfiable, you will never get there. Fine. Yeah, that's a little bit what the model checker does for you. So you instrument your code, you run your model checker, and you get your answer. Simple. And you only have 17 of those, so it's doable, right? So after 3 days, we analyzed those issues, one after each other, and most of them, if not all of them, were of the kind of, yeah, okay, it's safe, we can do this. It looks a bit weird, it's probably making some people nervous, not C programs, so this is all fine, you can do this. Now for the programmers, then this is done. Oh, this is fantastic, this is good C code, we know it works, ship it, right? But from a management point of view, in which role I also sometimes am, from a management point of view, say, okay, and if there's a little change in my program, in the C program, and I take the next version, what is my job? My job is to run the C analyzer, get another 17 or 16 or 18 issues, and analyze them once more, another 3 days, if I'm lucky. And if I then take the next version, another 3 days. I get a bit annoyed by that. But there must be a good reason for C programs to write code like this, right? It's not because they are incompetent or lazy or they just want to show that they know how to write C code. No, there must be a good reason. One of the reasons could be insecurity, that you actually don't want to have the time-dependent code, right? So some things have to execute in constant time, otherwise you have time attack. You can just look at how much time does it actually take in order to find out something about your code. So it might be that those really smart programs, they have actually looked at that and say, no, I can change my code such that that kind of time attacks are not at all in the picture. Makes sense. So there is an article published recently where people said, yeah, that makes sense, right? So let's write a lot of code that C programs would write, which shows them that there is no time attack. This is all constant time. And then run different compilers on that same code and show whether or not there is a time attack possible. So they compared a number of, they wrote some C code, which is all kind of constant time operations here, right? So if you look at this, that's constant time. And then they had a number of compilers and a number of versions of libraries and stuff, and they run that and you see, well, sometimes, mostly if you're inline and optimization of the compiler, if you optimize too much, then you have actually the possibility to do a timing attack, even though it looks pretty much constant time code. So you spend a lot of time to write your code precise, and your compiler is messing it up and optimizes it, and it's not constant time anymore. So they did probably think of this, but then you have to write the right options in your compiler when you compile your code in order to make sure that everything works. You get nervous again. Did I use my right options? Right? Did it actually work the way they expected it? I can tell you there were not many comments in the code that told me that this was done because of this or this reason. So this was a bit of problematic. So if you look at what we were doing, we use only, as I said, a very limited set of functions from that libsodium library. From Erlang, eNoise, we call eNaco, and then we call the libsodium functions in there. And it's only a subset, so this is not much. And the Microsoft guy, he had worked on a project where they wrote NaCl or libsodium, and they called it HACL. And that version was written in C, but it was not written. It was computer generated from the proof that it was correct. You can do these kind of things. You make a mathematical proof, and you generate C code from that, and you know that that C code has certain properties. For example, non-interference, no constant time attacks, and all that kind of stuff. So the code was by definition secure because they had generated from that proof. Super cool, right? Could we then use that code instead? If we could, that would be nice. And most of those things were actually implemented already by them. So only the generic hash they hadn't implemented at that moment in time. And you can say, oh well, implement that, but you can't because they have to write a mathematical proof that's correct. So they cannot just implement that, but we thought we want to test anyway that this will work. So we replaced all the functions we didn't use in libsodium by their functions, their C code, which was proven to be correct. Can it be nicer? So what you do, if things are proven to be correct, you of course want to still run the same kind of tools on that kind of code. So I say, okay, let's replace it, but also let's look at the C code the same way as we looked at libsodium. And surely I get 0 warnings, right? Well, that's true, but the formally verified code still gave me 4 bugs. Or issues, or whatever. Well, not really bugs, but it's identified 4 issues. But those were super simple, because they were all dead code. So we could immediately take the code away, and then we had no issues anymore. So that was kind of easy. So I could say, well, fine, if it is that good, we could probably use it. So, formally verified code, only 4 issues, take the issues away, still passing all the tests, formal verification tools said, oh, this is still fine. So that was perfectly well. What happens then? What do you do if you get formally verified code and you run that in your system? You test it. No, you don't need to test it. It's already formally verified, right? It's proven to be correct. Well, coming from a certain school, I still wanted to test it, right? So we test everything with QuickCheck, which is a tool for automatically generating test cases from given specifications. So give it the specification. Specification is simple. It says if you encrypt something and you decrypt it, then it is the same. And everyone can come up with that kind of thing. And then you just run QuickCheck and QuickCheck says, oh, well, we'll do this for you. And it generates test cases to actually do that. And bang, you got a failure. It says, oh, no, this is not true. You can encrypt something and then decrypt it, and actually it will fail. That was a pity. So first we thought, oh, that must be in the eNaco layer or something like that. But no, it turned out to be in the code of this researchers that had made everything. They proved the whole thing, apart from what they did is they mapped their function names to the function names in libsodium such that they would be replaceable, right? And this is their code, so they do have a crypto sign open, but crypto sign open has that name in libsodium, but in their library it was called Hackle ED25519 verify, of course, right? So they just mapped this with the data types to something else with the data types, and then had a result. And then if the result was true, they would say memory move blah blah, and otherwise they would say false. So they check your sign and signature, and you say true, okay, your signature is true, false, okay, your signature is false. With that little twist, that in C, true and false can be defined 0 minus 1, or minus 1 and 0, and they have the wrong representation of true and false. So whenever they would say true, it was actually false. Whenever they would say false, it was actually true. So whenever you would say, is the signature correct? It would say, yeah, it's correct, even though it was wrong. And so we said, no, it's not correct, if it was correct. We found that very quickly with testing because that's not a very hard thing to find. Then I also saw this kind of small code snippets which I didn't really say. Did you also prove this to be correct in memory saving? No, because that was outside this code. I said, okay, fine. You have something to do before we actually put this in. Moreover, I was running this from a branch with a name which was a bit suspect. It was not master. It was more like work in progress to be done by blah blah. So this was kind of not really mature stuff. So it's a good backup. We want to use this in the future, but not now. We stick to Lipsodium, which we have analyzed. Okay, next level. eNuckle. eNuckle is written in the NIF framework. Anyone here used NIF? NIFs in Erlang? Few people. So if you want in a language like Erlang or any high level language to talk to a low level language like C, you have to make an interface. Right? And that interface has to be not messing up, basically. And since Erlang is a virtual machine, the risk is always that you crash your virtual machine by calling some C code which then crashes. So you have to make absolutely sure that the C code does not crash. Because then you can, in Erlang, can just recover if something would be wrong, but you cannot crash your Erlang virtual machine. And when you go to C, there's something called core dump, which I get all the time, and other people never. But that's typically something that in C would happen now and then. If the C does something weird, then it would just core dump, and there you are. Completely different from Erlang. Good, so we analyzed that. We use the same C because this is C code, right? And a little bit of Erlang. And the C code we analyzed, and this is Jesper, right? Jesper, who's only one finding, and he did copy and paste here, shifting this right, and because the code looks so nice, he also shifted on the last one, but hey, the value is actually never used afterwards, so this shift is absolutely not necessary. And the C-line analyzer finds that and says, oh, you do something extra, and that might be suspect. And taking that away was not a big deal. And then, so that was the only thing that our C analyzer could find. But we wanted to dive deeper into this, so we looked also in the actual code that was written. And the code looks always kind of the same. You have your function name that you would call from Erlang, more or less, and then it would check a lot of arguments. So you give an Erlang argument, well, you give C arguments, but they come from an Erlang world, and you have to inspect a little bit what the boundaries of those values are, and then you do something with memory here. So here you just check the arguments. Here you check that the int size is less than something, and you allocate memory. Here you allocate your actual memory, you do your crypto operation, and then you free your memory. You also want to check that you don't have memory leaks and that kind of stuff. So we really wanted to carefully inspect all that code, which we did. And so you allocate memory and you deallocate, and you go a little bit further and have a slightly more complex example here, the scalar multiplication, and here you have the checking of the arguments, and here you do a mem copy. So you start copying from the C memory into another part of the C memory, then you do some operations, and then here you zero out the copy, but you never zero out, of course, the original stuff, but you zero out the copy, so there is no trace even in the C memory part where you have used your keys or whatever you want. But anyone see this suspect thing here? C programmer, see it?
I told you I'm not happy.
Oh, okay, I'm not happy. Oh, well, I can tell you. So the zeroing out is okay. It's strange in an Erlang setting, but it's fine. You check everything, that's fine. But what's not so fine is 31 over there. Yeah? So if you have a hard-coded offset, then that might not be super nice, because it means that you have to be sure that this one is larger than 31. And there's already said here that this is the last one, clear the high bit, so this is the most significant whatever. So this is most likely an array of 32, and indeed it was a 32 byte array. But since you have 31 here and this is a constant, if you were to change that constant, you would probably get into trouble. So it would be better to actually look at the last one and change that code into this constant -1, and then everything would work. And the compiler would optimize that anyway. So that's the kind of things we found in that part of the code. And otherwise, it's just beautiful code and small things you find. It's put me thinking, Doc. So, Erlang users here, people writing Erlang code, or Java for that matter, probably Java you can do it. But, so the crypto is always very concerned about zeroing out memory. So they do something in memory, and then there's a key kind of in memory, and then they override to the zeros, and then they go back to the normal state. You can't do that in Erlang. Erlang has no idea of zeroing out something. It's just, you pass it in, and it will be garbage collected later on. But there's no zeroing out. Now, this is absolutely no problem for us, because there's no intruder on our nodes, that's assumed, that can actually look at the memory. So even if you get a crash dump on your node or whatever, you will be safe, because no one is actually looking at the memory. Okay? It's fair enough. If people cannot get to your machine, then zeroing out memory is not such a big deal. Unless you probably run in an Amazon cloud. Or unless you probably send your log files with your crash dump over the internet to some operator that can have a look at it. Yeah? So you have to be a bit careful there what you're doing. But we basically, since we don't really store any important keys in that one anyway, so it was considered not an issue. Yes, we cannot zero that out in there. Okay, then eNoise, Erlang implementation of a protocol. The protocol is very nicely specified. In short, it's more than one protocol. It's a protocol suite or a framework or whatever you call it. But it has a certain kind of formal specification of what it is doing, saying, oh, you send a message here, and then you answer, and then you send another one, and you answer, and then you have an established connection. And these are formal proofs of each of those kind of schemas that you can use for talking. And we use this schema, XK, I think. And we run through this formal analysis tool and said the schema itself is safe, and it has one red flag. They say, well, but only if the other session, if the session is completely completed. So when you start talking, you must wait until you get an answer in the end before you do something else. And we do that. So this is the thing. You can only start sending data when you have received the first data from the other party. So the initiator should wait until it gets the first data, and not the other way around, because then there is a risk of some kind. Code inspection, we do it that way. Then the question is, did we actually implement noise correctly? So we have an Erlang program implementing this nice framework. And we did that by extensive testing, QuickCheck of course, other tests as well, test factors such as cryptography was right, and code inspection. And the code looks almost one-to-one to the formal specification, because that's what you get if you have a functional specification almost, then you can just one-to-one copy that. So there was kind of, by code inspection to be correct. We could do better, but for the moment that was good enough. And then we had a look at also the layers where we used this stuff, and we looked in particular on how the key handling was done there in eNoise. And this was half a year ago, far before we actually got it live. But one of the things that we spotted then at that time is places where we kind of leaked keys. Where can we kind of leak keys? Because we had seen that before. We leaked keys to log files, for example. If you write in a log file, and you're, oh, this is my private key, by the way, and you write it in your log file, then that's not really nice, right? And that can happen. I mean, if you are working on something and you have a big data structure, and you say, you know, this big data structure, I want to dump it to disk, and then if something goes wrong, I want to have a look at it, and the key is in that data structure, you leak it to your log file. So I anonymized a little bit who will what, but there are a number of commits here going on, and you can see they're on different dates, and together they introduced a security leak. And it triggered, because I saw this security leak, you can also see it here. So we have a pub key here and a secret key. And this is airline code for those that don't recognize the meaning. So you have a secret and public key, and this secret key is then here, local peer. This is put a local is locked to epoch sync info. So this is where you lock your, or here, where you lock your secret key to disk. Not very good. So you look at the code and say, how on earth could we have missed that in our double peer review? Because we always have double, whenever we do a commit, two people are looking at the code and say, yes, this is fine. How can we miss that? And that, if you look at the commit order, you can see it. It's really sneaking in. And you only see in the commit, you see the line above and the line below. So you cannot always see where the things are used. So you say, oh yeah, well, they won't have the secret key. Well, that's fine. I don't see any harm in that, without seeing that line that you actually put it in there. So things can sneak in. So what we need is tools to actually find these kind of things, right? That you search for the keyword key, but that's not enough. But some kind of static analysis where you actually find those keys is an important thing to have. Oh yeah, this is the order of how things happen. So this was happening first. First someone says, oh, I need a local peer, and that has a secret key and a public key. And then the next one says, it would be fantastic if I could log that. And if you just write this, then you only see this line and that line in the diff, and you have no clue that there's a secret key in there. So it's tricky. Another sneaky leak of private keys was in this one. Not sure if you see it, but here you have your private key, and then you do a detach and a try and catch. And a try and catch, perfectly fine, but since you have a priv key here as an argument of that function, if you then catch that, you write a stack trace into an error, then it is in that stack trace, because you've called the function with that as an argument. Another place where you can leak keys. Manually, we went through the code and we got those kind of things, and we also changed the key handling. The keys are not anymore on the system, the keys of the accounts. We have still this communication key, but that's only there for a short time, and it's not really harmful if people would get it. But thinking about this makes you aware of a lot of those issues that you have to be attentive to. So, to conclude this, it was real fun, absolutely, to do this.